also thought that the ratio was 1 because there weren't enough new mu's rather than more new e's. Now, at the same time, as the detector was being built, everyone was starting to wonder, why is it that if new mu's are less than expected, maybe they disappear? So how would they disappear? And one possibility was suggested by an Italian physicist, Bruno Pontecorvo, who suggested that neutrinos of one type, or one flavor, could change to another flavor when traveling over some distance. Now, this is quite something that, you really want to suggest something like that? Just think, you start in say a Honda and you end up with a Mazda after traveling some distance. Well, so how did it suggest this could happen? Well, each one of our 3 flavors, he suggests, is made up of 3 components, nu1, nu2, and nu3, with masses that are slightly different, m1, m2, and m3. And what it is that makes a nu e, a mu, or a nu tau is the different amounts of nu1, nu2, and nu3 in your neutrinos. A nu e has a definite recipe for it to be a nu e, and so does a nu mu, and so does a nu tau. So for instance, a nu tau has a lot of this nu3 denoted in green. A nu e has very little of it. Okay. Now, how can that cause oscillations? Well, we're dealing nowadays in a quantum world, and particles, such as the nu1, nu2, and nu3 components, can be treated also as waves. Now, waves of particles of different energy or masses have different frequency. That means that per second, they go up and down a different number of times. Now, we're lucky, nature has been very kind to us in that instead of 3 neutrinos at a time to understand oscillations, we can deal with just 2. Okay? Not always the same 2, depending on what we're doing, but 2 is enough to get almost the exact result. So what happens when 2 waves of different frequency mix? Well, I can't produce 2 neutrino waves. So instead of that, let's deal with sound. Okay? So here are 2 tuning forks. This one I've modified a little bit to have a slightly different frequency from this one. Okay? So if I hit this one, you can hear a continuous sound. It decays with time, of course, but it's continuous. So is this one. Okay? Now let me hit both of them at the same time. Do you hear the wobble? Okay, so the sound is no longer continuous. It changes with time. So the loudness is when you have 2 crests at the same time, or the 2 waves, and the no sound is when you have a crest and a trough. Okay. So your perception of 2 waves traveling at the same time changes with time. All right. So let's now look at our nu1 and nu2. They're denoted by the red and the yellow waves here, and you see the yellow one travels a little bit, has a higher frequency than the red. And let's suppose that this mix of yellow and red is exactly what gives you nu mu. Well, after a while, you see that the mix is no longer exactly a nu mu. So to account for this different mix, you have to add in a little bit of nu e, for instance, with its own particular mix in the right proportion to account for this new mix. And then after a while, you might get back to the exact nu mu. So the mix changes with time, and now if your neutrino interacts in your detector, if it happens to hit your detector right at the beginning of its life, you're sure to get a nu mu. But if it hits your detector sometime later, you can no longer be sure to get a nu mu. Sometimes you'll get a nu e, sometimes you'll get a nu mu. And that is because of the probabilistic nature of quantum mechanics. So you will get the nu mu with this probability and the nu e with this probability. So in the oscillation formula, what you need to introduce, of course, is a way of getting when this maximum oscillation occurs and a way of understanding how much of the nu E will appear. Well, let's try and understand how, go one step further. Here are two waves and in this case, M2 and M1 are different, so the frequencies are very different. So obviously, the waves are so different that you don't need to travel very far before you change the mix very, very much. So the mix changes over even a small distance. If now, on the other hand, I have two masses which are very similar, so the mass difference is small, the frequencies are practically the same, and you're going to have to put your detector very far away to see a significant amount of oscillations. Okay. So in your oscillation formula, obviously, the mass differences will appear, M1 minus S2, M3 minus M2, and of course the third one, but this one you can calculate from these two. And there'll be three other parameters that will tell you how much is oscillating. And they're denoted by three parameters, theta 1, 2, theta 2, 3, theta 1, 3. Okay. Fine, so discovery of oscillations. The big detector finally came into being. 41 meters high, 40 meters across, a cylinder.